All right, today we are jumping right into the L in solid, the Liskov Substitution Principle. Now, this is the principle that really gets to the core of what makes inheritance work the way it's supposed to. And it stops our code from becoming this minefield of unexpected bugs. But let's start with a little puzzle. We all learned in geometry that a square is a rectangle, right? I mean, it's a special kind. It's a simple, intuitive is-a relationship. So why is it that when we try to model this very simple idea in our code using inheritance, things can just go completely off the rails? Keep that question in the back of your mind, because we're about to find out exactly why. You see, the problem is something I like to call deceptive inheritance. It's when our code's structure, the inheritance tree, it looks totally correct on the surface. You know, a square inherits from a rectangle. Makes sense. But what it's really doing is hiding a behavioral trap. It's creating a relationship that promises one thing but delivers something completely different, and that leads to some really nasty surprises. So how do we avoid these traps? Well, that is exactly where the Liskov Substitution Principle comes into play. The best way to think of it is as the official rulebook for inheritance. It's not just about what a class is, it's all about what it does. It's about setting up a behavioral contract that absolutely must be followed.
Okay, here it is. This is the formal academic definition from the brilliant computer scientist Barbara Liskov. And yeah, it is precise, but it's also pretty dense. So don't worry, we're not going to spend the next 5 minutes breaking down a mathematical proof. Let's get to what this actually means in practice.
And here we go. This is it. This is the golden rule. If you remember only one thing from this whole explainer, make it this. Wherever you're using a parent class, you should be able to just swap in an object of any of its child classes without the program breaking or even noticing the change. The behavior has to stay correct and predictable, period.
So, the most crucial point is this. LSP is all about behavioral consistency. Look, a subclass can add new methods. It can add new features. That's totally fine. But what it can never, ever do is change or violate the behavior that was already promised by its parent class. It has to honor the original contract.
You know the classic duck test? Let's use that to build some intuition here. A real duck, it has a certain set of behaviors, right? It quacks, it swims, it flies. Now, what about a toy duck? Well, it might look like a duck and quack like a duck, but it needs batteries. That one little detail, needing batteries, is a huge behavioral change. If your program is expecting a duck but suddenly has to stop and check for batteries, then that toy duck is not a valid substitute. It has broken the behavioral contract.
Okay, so let's circle back to that puzzle from the beginning. Now that we understand LSP is all about substitutable behavior, we can finally take apart that classic square rectangle problem. First, let's define the contract of our rectangle class. Any piece of code that uses a rectangle object has an expectation. It expects to be able to set the width and the height completely independently from each other. Setting the width should not affect the height, and setting the height should not affect the width. That is the behavioral promise.
And here's the violation. Our square subclass inherits from rectangle, but to stay a square, it has a rule of its own. The width must always equal the height. So it's forced to change the behavior. When we call set width on a square, it has to change the height too. It has fundamentally altered the contract that it inherited.
So let's imagine we have some client code. Maybe it's a simple function that calculates the area of a banner for a website. It's designed to accept any rectangle object. It sets the width to 5 and the height to 10, and it is fully 100% expecting to get an area of 50. It's relying on that independent behavior of set width and set height.
And here is where it all falls apart. We try to substitute a square object into that function. The function calls set width to 5, which also sets the height to 5. Then it calls set height to 10, which also sets the width to 10. The function expects an area of 5 times 10, which is 50. But what does it get? 10 times 10, 100. The behavior is totally unpredictable. The result is just wrong, and our substitution test has failed big time. A square is not substitutable for a rectangle.
Now, this might seem like just a simple, quirky bug, but these kinds of LSP violations have enormous consequences for the overall health of our software. They are one of the main causes of software rot, leading to systems that are fragile, rigid, and just a pain to work with.
So when we violate LSP, polymorphism, which is one of the greatest benefits of object-oriented design, it just breaks down. We can't trust our abstractions anymore. And what do we do to protect ourselves? We start littering our code with type checks, right? Asking, if this object is a square, do this. Otherwise, do that. And this just kills extensibility. The whole system's behavior becomes unpredictable, and trying to write clean, simple unit tests becomes an absolute nightmare.
Here is a really powerful way to think about it. The open-closed principle, OCP, tells us our systems should be open for extension but closed for modification. We should be able to add new subclasses, but what makes that safe? LSP is the answer. It's the seatbelt that makes sure our new extensions, our new subclasses, don't crash the entire system when we plug them in. It guarantees they'll play by the established rules.
And believe me, this isn't just for high-level application code. Let's take a look at one of the most robust, most critical software systems on the entire planet, the Linux kernel. The spirit of LSP is absolutely fundamental to its design.
So let's see how these concepts map. In the Linux kernel, the client is the virtual file system, or VFS. The superclass contract is actually a C struct full of function pointers called file operations. And the subclasses? Those are the actual file system drivers, things like ext4 or btrfs, that all have to implement this exact contract. And the behavioral contract here is completely non-negotiable. For example, the read function in that contract has a very strict rule. It must return a specific value, -e again, if there's no data available right now. If a new file system driver were to break that contract and return 0 instead, the VFS client would misinterpret that as end of file, trust is broken, and the entire operating system could fail in subtle, silent, and catastrophic ways. At this level, LSP is literally the lifeline of system stability.
Okay, so we've seen the theory, we've seen the high-stakes examples. How do you actually spot these violations in your own code? Well, let's look at a few of the most common code smells.
First, if you see a subclass that overrides a parent's method but then just leaves it blank or throws a not implemented error, that is a massive red flag. You know, an ostrich subclass can't just do nothing for the fly method it inherited from bird. Another big sign is a subclass that throws a new kind of exception that the client code isn't prepared to handle. But the most blatant signal of all is seeing code that explicitly checks an object-specific type. That if instance of check is basically a written confession that you can't trust the base class contract anymore.
Look, mastering LSP really requires a fundamental shift in your mindset. You have to stop thinking just in terms of is-a relationships, like a square is a rectangle. Instead, you have to start thinking in terms of is-substitutable-for. Can this object be safely used anywhere its parent is expected without causing any surprises? That is the only question that truly matters.
And that leads us to the final and most critical question you should always be asking yourself. When you find an inheritance relationship that feels right on the surface, but breaks behaviorally, that's a sign. It's forcing you to ask, is inheritance really the right tool for this job, or is it maybe time to solve this problem with a more flexible approach, like composition? It's definitely something to think about on your next project.